Hey everybody, welcome to Alabama Biodiversity. This is BI 101 Explorations in Biology with Dr. Duncan. So I'm going to pick up at the last class that we were in the middle of before the pandemic break, which was class 12, Evolution Part 4. And we're in an exploration of what's called deep time. That's basically Earth's long history from 4-point-something billion years ago up to the present day. And our goal here is to understand how the things that happened over these long periods of time influence the Alabama landscape today, creating that landscape and also populating it with so many interesting species. So let's get started. First of all, there are these three reasons why we've got so many species in Alabama. It's our warm, wet climate. It's very lush and great for ecosystems and lots of plants to grow and animals to thrive in those ecosystems. Secondly, we've got a tremendous amount of geologic diversity compared to other states. We've got lots of different rock types at the surface of the earth, and they create different types of soils and therefore different ecosystems. And then finally, we've got our evolutionary and geologic history. And these two ideas of geologic time and evolutionary time, they are interwoven because the geology, as it's changed on our planet, has shaped what biology lives on the planet, and hence therefore shaped evolution. And at the same time, evolution has shaped the geology. Different types of rocks on the Earth's surface, for example, are created from living organisms. So we've got that interplay, and it's really fascinating. We'll be exploring that as we move forward through time here today. So it all begins a long time ago, so long that we divide up time into these multiple stages. And we're going to start off in the Hadean, the time period right here. Let me get my little laser pointer going here. The Hadean, way down here at the lower right-hand corner of your screen. We're going to start off at about 4.6 billion years ago. Now, you do need to memorize some of the times that you see in this diagram. Refer to the previous class for notes on which of these time periods you need to memorize and which dates and so forth. But suffice it to say that we're going to start here now at the Hadean and move our way through time. So we're going to start here at the lower right. We're going to move through time up this scale up to here, and then the scale switches back down to the bottom left here, and we're going to move up through this to modern time, which is right up here in the Quaternary period, which is nested within the Cenozoic era. Okay, that's our framework. Let's get started. So our solar system began a very long time ago, a collection of gas and dust in the interstellar space, collecting around a central gravity well that later became our sun. As that dust accumulated through gravity, it formed planets and then moons and so forth and so on. All of that is beyond the scope of this course, but absolutely fascinating to look into. But this is what things here in Alabama would have looked like at about 4.6, 4.7 billion years ago. Once our planet was formed, it was a very squishy place for a long period of time. And during that time, we call it the Hadean. You probably note that term sort of is a reference to Hades, which of course is the reference to I think it was the Greek underworld or hell. The planet at this time was basically inhospitable for life. We were no longer a gas cloud, but the material that had come together because of the force of gravity and the pull of everything together, it was all molten liquid hot. So we had the Earth's surface was basically pockmarked with volcanoes erupting all the time. It was too hot for things to cool down, so these materials would just keep melting and then cooling and then melting and then cooling, and it just stayed like this for a long period of time. Must have been pretty awesome to see, but certainly not a place where we would survive for very long. So that span lasted from 4.6 to 3.8 billion years ago. Now let's move forward to later in the Hadean, that same time period, when Earth finally began to cool. And as it cooled, water was released from the the elements, the minerals that had collected to form the planet. So when the planet was too hot, that water stayed in gas form. But once the planet cooled enough, the water was able to accumulate as liquid on the Earth's surface. So we expect that back in time, we went from that molten landscape to one that was mostly covered by oceans with still volcanic activity very abundant, but not quite as much as before. At this point in time, it's also interesting to note that there would be no reason to have oxygen in the atmosphere. There were no plants yet that were doing photosynthesis, so no way that oxygen could accumulate in the atmosphere. So if we were to magically transport back in time, or to use something like the time machine or something like that, we wouldn't survive but for a few seconds outside of our protective devices. Okay, now it was at the end of the Hadean that marks the emergence of life on Earth. In fact, we use the emergence of life as the beginning of the next time period, which you'll see over here on your far right, the Archaean. And this is referring to Archaean, referring to the Archaea, which is some of the more primitive forms of bacteria that we still have on the planet today. Now, this begs the question, of course, where did this life come from? And there are, as I talked about in class, there are three different hypotheses. One of which is special creation, which is not really a scientific hypothesis. It's more of a belief system that life was put on the Earth by a supernatural or divine force or forces. This, of course, is outside the realm of science. It's not something that's testable. There's no way to accumulate evidence for that and test hypotheses and so forth. So we just sort of acknowledge it and set it off to the side. Within the realm of science, there's two basic explanations. One of them is something of a cop-out, and that is the extraterrestrial origins, that life essentially evolved or developed somewhere else in the universe and wound up infecting Earth from another planet via meteors that carried that life to Earth. That's always something of a cop-out because, of course, you still have to explain how life emerged on that other planet somewhere far away. So ultimately, life would have had to come from a non-living system, a non-living situation, creating a situation where the very first chemical reactions that began to resemble life would have emerged. And I'll say as much that we've done a lot of science on this over the last century or so and come a long ways in creating life-like molecules and from situations that resemble these early Earth environments. And I'm not going to spend too much more time on this, but I just want to acknowledge that this is still one of the greatest mysteries in biology, one that we have yet to solve. And I think that's pretty cool because it keeps things, it's fun to have some mystery left. All right, so this is just some more details about these different hypotheses. I'll let you read those on your own. And this is in reference to two things. The top is some of the early first experiments to try to see if life could spontaneously form in the lab. And they actually have they never have created life from scratch in the lab, but they're getting closer, the folks that are working on that, which is really interesting to think about. The bottom picture is, of course, referring to where one of the environments on the planet that we think that life might have emerged for the first time, which are these deep sea volcanic vents that have lots of complex chemicals coming out of them in a very stable and energy-rich environment. Okay, so now we're moving on from the Hadean to the Archaean. So if you look down here at your lower right, you see my little laser pointer here I got going on here. This is the beginning of the Archaean at about a 3.9 or 4 billion years ago, and it lasted a long period of time, all the way up to about 2.5 billion years ago. During this time, we had the first life on the planet. We had, messing around with my tools here, hang on. So we had the first life on the planet emerge at the beginning of this time period. These were very simple organisms, much like modern-day bacteria. Some of these organisms we think are still around, though in modern forms that have evolved a little bit. This picture to the lower right, you see here the little inset says fossil bacteria cross sections. These are actual cross sections of the fossils that date back to the Archaean. We do have rock that dates back to this time period. And you'll notice here in the lower right, let me get my pen going on here. You'll notice these mushroom-shaped structures that we have here on the screen. These are called stromatolites. Stromatolites are not living organisms, but they're basically colonies of these primitive bacteria-like organisms that are growing together. And as they do their thing, as they live, they secrete waste materials just like you and me, and those waste materials wind up building up this solid form like a rock. And that rock that is formed is called a stromatolite. We can see stromatolites in a few places in the world today. They still exist. This is a picture from Sharks Bay, Australia, where we see these stromatolites. So if you ever want to go back in time without actually traveling in time to see what the early Earth might have looked like, save your money, go to Sharks Bay, Australia, and you can get a glimpse of what early life looked like on the planet for a long period of time. Not how I would spend my one ticket to go do some time traveling. I'd rather go see something cool like dinosaurs or mastodons or something like that. Anyway, moving on here. Okay, this is a picture of a stromatolite. One of the things I think that's cool about them is that you can find them here on campus. Anytime you see any rocks that are up at the surface that are natural rocks, like from the local landscape, you can find these bands, these color bands in those rocks. So those are basically, you're looking at cross sections of stromatolites. Okay, the next time period is the Proterozoic eon. So now if you look at our chart to the right, we're right about here at about 2.5 billion years ago. And that lasted from basically about 2 billion years, as you see here. That is a long, long period of time. And during this time period, life on Earth was still pretty low-key, lots of bacteria and simple one-celled organisms in the oceans of the world, nothing on land yet. But during that time, we see that oxygen does accumulate in the atmosphere, and that tells us that, that plants had developed photosynthesis, that these single-celled organisms living in our oceans were turning sunlight into sugar, and a byproduct of that was oxygen. So you can go back to earlier classes in the semester where you talk about photosynthesis, and we talked about the chemical formula for photosynthesis, and you'll remember that oxygen is a byproduct of that, and that's very good for us animals because we need that oxygen in order to survive. Okay, so during the Proterozoic, one of the things that happened was that you had the continents of the world began to grow. So you had enough cooling of the planet and the geologic processes deep under the earth were allowing more and more land to show above the surface of the ocean. And those grew into the continents of today. And in these maps that you'll be seeing, you'll see like the shapes of the different continents of today imposed on them. So for example, here's Australia. This shows the modern outline of Australia in white. The part that you see here in brown, that's the part of Australia today that dates back to this time period, which in this case for this picture was 650 million years ago. So if you go to Western Australia, you'll be standing on rock that formed 650 million years ago, which is, I think, pretty amazing. Notice that the planet's like really stretched out like that. That isn't because the planet was shaped like this. We didn't have these ends sticking out into space like this. This is just a way of mapping in order to show you much of or all of the Earth's surface at once. Okay, the final thing here is to just point out that the Proterozoic came to an end when a large collection of land continents wound up breaking up. So this supercontinent that had sort of collided here broke up at about 545 million years ago. Of course, that breakup went over the span of like tens of millions of years, but that marks the end of the Proterozoic eon. Okay, so that wraps up part one of our exploration of deep time. We'll pick up again in our next segment.